Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be talking about some quick examples relating the degrees of freedom of a system and eventually leading to a discussion on the Lagrange equation of motion. Okay, so what we have is we would like to find, so I directly start with an example. So find the degrees of freedom for a simple pendulum. Well, for a simple pendulum, if we look at how the pendulum moves, this is going to be a bob which is hanging from the wall at a fixed distance A, and then the angle that the bob makes with the vertical is going to change with time. So we have the angle theta, and so theta is what the degrees of freedom for this simple pendulum is. So we have an answer 1. So the answer is theta. Okay, so then how about the case of spherical pendulum? The case of spherical pendulum, we have two degrees of freedom, because this time the pendulum is moving on the surface of a sphere, right? So it is moving on the surface of a sphere and surface of a spherical shell. So we will have two angles theta and phi, right? And then we have how about the case of a door swinging on its hinges, right? So we have, what is the case? We have a door which is swinging on its hinges. So we have an angle theta, which is the angle that the door makes with respect to, let's say, the horizontal. So we have the angle theta here. Okay, so then the fourth case is that of four rigid rods. No, so we have one more example: a bar of soap sliding on a basin. A bar of soap sliding on a basin. So again, the basin could be seen as a hemispherical shell, and the bar of soap, when it is sliding, it is going to be defined by two angles or two variables, which are again theta and phi on the surface of the sphere. So this is going to be theta and phi, right? And then we have four rigid rods flexibly jointed to form quadrilateral, right? So again, we have four rigid flexible rods jointed to form quadrilateral. So we have, again, the rods are at a fixed distance, the points are at a fixed distance from each other, and all we expect are the angles theta 1, theta 2, theta 3 and theta 4, which are going to completely describe the motion of the quadrilateral. So the answer is, we have 4 degrees of freedom, and so on. And then we have another example where a ball is rolling on a rough table, right? So we have the ball is rolling. So the moment we are involving the rolling, we are involving the kinematic constraints, involves the velocity. So we cannot describe as to how many coordinates will be needed to describe this system. So this is going to be, the number of degrees of freedom will be undefined, and so are the number of generalized coordinates in this last example. So then So then what we have is, the case of a circular. We have, let us look at one more example of a problem involving geometric constraints. So what is it? So it turns out that even kinematic constraints for certain cases are not a problem. Why? Because kinematic constraints which are integrable, kinematic constraints which are integrable, right? Cannot Which are integrable, they give us geometric constraints, and then in that case the problem, it is easy to find the degrees of freedom of the problem once we are in the geometric constraint category. Okay, so what we have is, so this is one point. The other point is that kinematic constraints themselves, they cannot be added by some new they cannot be added by some new set of generalized coordinates. They must be involved as an extra equation along with the equations of motion. So what I just said is that kinematic constraints must be added by some new must be added as an extra equation as an extra equation and typically they cannot be added as a generalized coordinates. Okay, so let us look at an example for the first, involving the first statement, as to how we can use integrable kinematic constraints. So the example that we have is a circular cylinder rolls down a rough plane, and we need to show that the rolling condition is an integrable constraint. Okay, so the moment we are saying a cylinder is rolling down, so let us say this is a cylinder which is rolling down a plane. So let us say that the displacement of the cylinder is x. So x being the displacement of the cylinder axis, the displacement of the axis. Then let us say we have the theta being the rotation angle. So the cylinder is being rotated by an angle theta. So theta is the rotation angle. So what we have is that the rolling condition is given by x dot is a times theta dot, and what we get is that so this is my rolling condition, and we can easily integrate using some initial condition. We can assume that the displacement x at t equal to 0 is 0, and also theta at t equal to 0 is 0. So the cylinder has not rotated and it has not moved any distance at t equal to 0. So we can integrate, we find that x is equal to a theta, and we get a geometric constraint from a kinematic constraint. So now we are in easy territory where we can continue to solve the problem by introducing the geometric constraints or the geometric constraints. Okay, so this is one example where we are able to easily integrate and find the equations of motion, the geometric constraints. So now we have we have another problem in mind. The second problem is that of a non-integrable a non-integrable constraint. A non-integrable constraint. And this is a case where suppose we have a circular disk of radius a, and it is constrained to roll on a horizontal floor with its plane vertical. Then we need to show that the rolling condition are not integrable. Okay, so this is another example that we look at for the circular disk case again. So let us try and draw the diagram, that way it will be easier for us to visualize. So let us say we have this disk which is rolling on a plane, and let us also fix the frame of reference. Let's say the horizontal direction is I and the vertical direction is the Z direction K, and we have the third direction J, and let us say the point I, the contact point of the circular disk is making an angle theta, and theta is the angle with respect to the horizontal. So then what we have is that, let us say the contact point theta. So theta is so let us say the disk at any given point of time is also rolling. So it is rolling to give you a distance. So the total distance traveled by the cylinder will be x, the distance of the center traveled by the center of mass c, plus whatever is being rolled by the disk. So let us say at any given point of time the disk is rolling by an angle a phi, where a is the radius of the disk, right? So basically this diagram shows us that there are 4 degrees of freedom. 2 degrees of freedom are the coordinates of the center of mass, and the other 2 degrees of freedom are theta and phi, the angle with respect to the horizontal, and phi is the angle that this disk makes with respect to the disk rolls. Okay, so we have 4 degrees of freedom, right? So one set is the set x comma y, which is the coordinates of the center C, and the second is the angle theta between the plane of the disk and the x-axis, and the third one is the angle phi that the disk has rotated. So that's it. So then we can quickly, so based on this diagram, we can quickly write down the rolling condition. So what we have is that the contact particle should have 0 velocity. The contact particle should have 0 velocity, right? So the first case could be that x dot plus a times cos a phi dot cos theta. So this is my x condition. So this has to be 0, right? So this is the net velocity in the x direction, and the second rolling condition. So the contact point is rolling. So the net velocity will be 0 of the contact point. So because of the rolling condition. So we are writing the x component. So this is my x component of the rolling condition, and the y component similarly will be y dot plus a phi dot sine theta is equal to 0, and this is my y component, right? And so what we have is that we can quickly see that this star cannot be integrated since theta is an unknown function of time, and so is phi. So we have this, we cannot integrate this, it is quite easy to see, and hence we cannot retrieve any geometric constraints for this problem. So no geometric constraints of this problem. Okay, so then what we have is, let us now look at another classification of the constrained motion, the so-called holonomic and non-holonomic systems. Holonomic and non-holonomic systems. Okay, so what we have is, so let us quickly go with the definition. So if a system has only geometric or integrable kinematic constraints, then it is holonomic, otherwise non-holonomic. So if a system has only geometric or integrable kinematic constraints, it is said to be holonomic. If it has a non-integrable kinematic constraint, then it is non-holonomic. So non-integrable kinematic constraint, then this is non-holonomic. Okay, so then let us talk about the configuration space or the Q space. So this is, again, the configuration space is the space of all the generalized coordinates. So configuration space. So we are slowly coming to the case of Lagrange's equation of motion. So that is what we want to focus our attention. So configuration space. So again, this is also known as the Q space, or this is the set of all the space governed by the vector of generalized coordinates, right? So this is the Q space, Qi. Okay, so we have, let us say we have the definition of the generalized coordinates. So let us say we have the definition of generalized velocity. So that is what we want. So the time derivatives q1 dot, q2 dot, and so on, qn dot, of the generalized coordinates q1, q2, qn are called the generalized velocities of S. Okay, so what we have is the time derivatives of the generalized coordinates. So for example, let us look at the case of position or the particle velocities. The position or the particle velocities, they can be found from Qi or Qi dot themselves, right? So what we have is that Ri is Ri of Q, right? And typically my Vi is, well, Vi will be partial Ri partial Q partial T, or this is also in terms of partial Ri dot partial Qj times Qj dot. So this is summation over j. So in terms of generalized coordinates, we have written the velocity, and this is what we have. Okay. So then what else we have? So we would like to find the particle velocity for two particle system. So let us now look at this idea of introducing this velocity in terms of generalized coordinates through some example. So the example is, find the particle velocity for two particle system in example 2, and deduce the formula for the kinetic energy for the equal mass case. Okay, so we have the particle velocities are given as v1, this is x dot I, and v2, which is x dot I. So this is the case of the example 2 is the case of the two particle system, one of which is moving horizontally and the other particle is connected to the first particle, which is allowed to rotate vertically. So it has the set of two generalized coordinates, right? So this was the example I'm talking about. So the moving and the rotating pendulum. So in that case, V2 was equal to, in this case, this is going to be x dot I plus a cos theta I plus a sin theta k, right? And this is going to be times theta dot. So then in this case, I can write down the kinetic energy. So this is half m v1 dot v1 plus half m v2 dot v2, right? And we get that this is also equal to half m x square plus half m. We plug all these formulas here. So x dot square plus a theta dot square plus 2x dot a theta dot cos theta, right? And this is also equal to, we do a little bit of simplification, so we get that this is the following: half m a square theta dot square plus m a cos theta x dot theta dot. Okay, so then what we have is we need to show that the system has kinematic. We have one more example that I would like to discuss. The second example that I have is, we show that the kinetic energy of any holonomic mechanical system has the form T, which is given by summation j, summation k, a j k, q qj, qk, right? This is a homogeneous form in the variables with coefficients depending on q. Okay, so v, in this case, v can be, so now we are going to show that the kinetic energy has this form, right? So to do that, Let us see that my velocity v has the form partial summation, partial r partial qj times qj dot, right? And if we were to find v dot with v, I see that this is going to be summation partial r partial qj dot and partial r partial qk dot, right? So we see that when we take a double sum, we see that this is also equal to jk partial r partial qj partial r partial qk. Okay, so we see that this is qj dot qk dot. And now if we were to write the kinetic energy, this is going to be half summation mi v dot with v, and we have that this is going to be the form we were searching for. This is coming out to be ajk qj dot qk dot. So we see that where my ajk's are half m times or mi times summation over I mi times summation over j, and well, I need to remove this summation, double summation. So this is partial ri, well, partial r partial qj times partial r partial qk, right? And this is going to be the case. Okay, so we have so this is the example that shows the form of the kinetic energy in general. We are going to wrap up our discussion by mentioning as to what sort of velocities we need so that there are no constraint forces appearing in the system. So we are talking about the so-called D'Alembert's principle and the so-called principle of virtual work, right? So the goal is to remove the problem of unknown constraint forces. Fi of C, and where I is between 1 to n, right? This is my constraint forces. So what have we got? So typically my second law is mi vi, which is Fi of S plus Fi of C, right? So this is my net forces, and let me call this as my equation number 1, and let us say that I take a dot product of this equation with some unknown AIs, and I would like to find such values of AIs so that work done by the constraint forces vanishes, right? So let my AIs of T be I from 1 to n, be any vector functions of time t, and we have that summation mi vi dot times ai. This is also equal to, we are taking a dot product, so this is Fi of S dot with ai plus summation Fi of C dot with ai, and we see that we need to make the work done by the constraint forces 0. So we want to make it 0, and we want to find such values of AIs, right? So this question we are trying to answer is, can we make Fi dot AI to be 0, right? And that is the point where I am going to end our discussion in this module. And in the next module, we are going to go towards the derivation of the Lagrange equation of motion. So thank you so far for listening.